Hello, this video is the fifth installment to the ray optics or geometrical optics that we had been discussing. And I remember having provided you with a question in the previous video, at the end of the previous video, where we had to prove that if we were discussing reflection, so we had to prove that if a mirror, which is causing the reflection, now this was the question. So if I consider this plane mirror over here, and there's a ray that is incident over it, and it's a straight line. It's not a straight line, but we'll assume it to be a straight line. And if it is incident at, let us say, at an angle of incidence being I, and the mirror now is rotated. Now, obviously, this will get reflected. This will get reflected obeying the laws of reflection. We have the angle of incidence to be equal to the angle of reflection. So this is the reflected ray, which has the angle of reflection as r, and I is equal to r as we know it. Now suppose we rotate the mirror. Now this was the normal. This was the normal drawn from the point of incidence. Let us take the point of incidence as O, and the incident ray as IO, and the reflected ray as OR. Now if the mirror is rotated through an angle theta, so this is now the inclination of the mirror. It was rotated through an angle theta over there, and so that angle will be also the same for the normal, which is now assumed from the point A. There's a point of incidence, and the normal will be rotated through an angle theta as well. Rotate it on the side shown or on the other side. I have considered it to be rotating in that sense. Now the initial position of the mirror, let's say, was a M1, and now it's M primed, M1 primed, and the angle of rotation is theta, and so is the case with the normal. Now the normal is, suppose, ON primed. Now as you can see, the angle of incidence in this case has reduced. Now it has reduced to I minus theta. What about the angle of reflection? Now the reflected ray, that will also be rotated. We are keeping the IO, that is the incident ray, to be along that line, while the mirror has been rotated. So there will be definitely some rotation of the reflected ray. The reflected ray, which was moving along OR, now we will be considering it because we have a new normal, that is ON prime, and the new angle of incidence. So following the angle of incidence, we have the angle of reflection, and the angle of reflection is r minus theta, and it's along OR dash. So that angle that we see over there is r minus theta, because I is equal to r, and theta is subtracted from both of them. So that's the angle of reflection in this case with respect to the new normal, that is ON primed. Now what about the case of the angle between the first reflected ray and this new reflected ray? We wish to determine the value of ROR primed. That is the angle of rotation of the reflected ray. Now here ROR dash, that we can see over here, that can be determined by considering few angles that are nearby. One of them being the angle theta, of course, that is the angle of rotation. But the easiest approach that we can consider over here is just to take the angle that was available at first. That is, we have N primed OR. Let me mark it for you in another ink so that it's clearly observable. So this is N prime here, and then we have O, and then we have R, which is this one. Now what is that angle? That angle is as you can see over there, that's a big angle. N prime O R is simply equal to r plus theta if you observe closely. This is equal to r plus theta because n prime has shifted through an angle theta from n, and r made an angle small r, that is the angle of reflection with respect to the normal n. So r plus theta over there, and then this is n prime or minus, what we need to subtract from it is n prime o r prime. N prime o r prime is going to be subtracted from it so that we can get the value of r o r dash. So this again, and the new thing that is to be taken into consideration is r prime, that line. So this angle that we are supposed to obtain, that is deflection of the reflected ray, initially was along OR and now along OR prime. The angle between them is to be determined, and how do we do that? Well, we consider this entire angle, and we subtract this angle. Well, that angle is quite known to us, that is n prime o r prime, and that is simply equal to r minus of theta. So what we have over here is r plus theta minus r minus of theta. If we remove those brackets, then we have minus r plus theta, and so r, they get cancelled out and we have 2 theta. So what we conclude is that for an incident ray remaining or maintaining its line and incident on a plane mirror, if the mirror is rotated through an angle theta, then its reflected light ray gets rotated through an angle 2 theta in any possible direction that we are rotating the mirror. Here I have considered a rotation in that sense, that is the counterclockwise sense. You can also try it in the clockwise sense and observe the deflection of the reflected ray. A typical question that is associated with the plane mirror, the reflection in case of a plane mirror. Now, as a person stands in front of it, and what must be the minimum size of the plane mirror such that the person is able to view his complete image in it? Now, here's the person who is standing in front of it. That's his head, the top of his head, and that's his leg. And supposedly just below the head there you have the eye of the person. Now for proper diagram, for proper viewing, I take the eye somewhere here so that it's easier for us to draw a highly magnified kind of approach so that the angles are clear. I'm redrawing the mirror because it's a messy, it looks a bit messy, so let me just erase that image first. So that's more or less the case. So in this case, the entire mirror will be used to view his complete image. So a light ray which must be striking his the top of the mirror over here, somewhere over here. This is the length of the mirror that is being considered. This much, not above that. So this is the length of the mirror that is being considered, and supposedly the light that is reflected from his head gets reflected towards his eye, and in that way he can view the top of his head, and the bottommost point of the mirror that reflects the image of his leg to his eye, and in that way he can view his image completely. That's more or less the case. So what must be the length of the mirror as compared to the height of the person? Now Let us say the height of the person entirely taken is h. So we are taking it as h, and this length that we'll be considering, let's just name the mirror as m, and then here over here it is m dash, suppose. So we need to calculate mm dash in terms of HL, that is the complete height of the person. Now, if we are considering the normal drawn from the point of incidence, those are the two normals that we have considered. So let's name them. We are naming this one as N1 and we are naming this one as N2. And these normals, if you observe those triangles that have been drawn about that normal, so this triangle HMN1, the top triangle HMN1, that's a right angle triangle, and we have a congruency over there where you have the triangle HMN1 to be congruent with the triangle EMN1. It's quite obvious because the right angles and the distances covered, they will be the same. HM will be ME. They will be equal because they are traveling almost the same distance as from the head to the eye. And then again you have those angles to be the same. So you have this angle, the top angle, to be equal to this angle because the angle of incidence is equal to the angle of reflection. You have these two angles to be at 90 degrees, so they are equal as well. So side angle side, you have a common side over there as N1M. So all of that adds to the congruency, the proof of congruency. Similarly, in a similar manner, although it doesn't look so, but you can have I can extend the leg a bit so that it's ideal because the angle of incidence here is not equal to the angle of reflection. So I can skip this line. I'm erasing that just to show you. Okay, now it's completely erased. So here also we have the same case where because of reflection you have the angle of incidence and the angle of reflection to be the same. The first one is the angle of incidence and this one is the angle of reflection in that case. And you have a common side N to M dash, and then again you have the other angle, that is the 90 degrees, the normal that meets the point N2. So similarly, you have the congruency of the triangle EM dash N2, and that is congruent with what? Now that is congruent with the triangle LM dash N2. Now, because of congruency, what you have is this length HN1 will be equal to N1E. So HN1 is equal to N1E. Similarly, EN2, that is for the triangle below, EN2 is equal to N2L. Now, HL, that is the total height of the person, that is equal to HN1 plus N1E plus N2 En2 plus N2L, all of that. Now what we also see over here is that MM dash, that is the length of the mirror, that is equal to N1E plus En2, right? Because of the normals that we have considered, they are exactly pointing towards N1 and N2, which are aligned with M and M dash respectively. So you have this. Now here you have 2 N1E, if I can take it. This is 2 times of N1E, and the other one, that is 2 times of En2 because of the congruency, right? And so what we have over here is equal to 2 times of N1E plus En2, or that is equal to 2 times of N1 and 2, and this is equal to N1 and 2 as well. So MM dash, that is the length of the mirror, is equal to 2 times of N, is equal to N1 and 2, and n1 n2 is actually n1 n2, therefore is equal to h over 2, because this was equal to h, so this is h over 2. So finally what we have is the length of the mirror must be half the length or the height of the person, so that the person standing in front of it can view his image entirely. Now here are two typical problems that we associate. So this is the first one, where we have an object, supposedly a person, who is moving with velocity v, and let's say that is VO, velocity of the object. And what he observes is that his image is moving with the velocity V dash, or we would say that is VI, and that is exactly opposite in direction to VO and equal in magnitude to it. Now, initially the distances were quite the same, that is L and L, as the person started off, and for himself as well as for his image. Now, as he moves, with what velocity would he observe his image to be moving towards himself? So that's relative velocity that we are to consider. So this is VIO, that is the velocity of the image with respect to the object. So this is Vi minus Vo, that is the velocity of the image minus the velocity of the object. Now, because we know that Vi is already is equal to minus of Vo, so this is a minus Vo minus of Vo, so this is minus 2 times of Vo. Now, velocity wise, obviously the person will observe that his image will be moving twice as fast as himself approaching him, right? And this is another question that I would like to leave you with at the end of this video, where we have a person from head to leg, H to L, and he is standing right in the middle of a room, of a square sized room, and his distance from the first wall over here is L, and from this wall over here is L as well. So these are the two lengths. So he's standing exactly at the middle of the room. Now there's a mirror on the wall to which he is facing. He wishes to observe the entire length of the wall. Let the entire length of the wall be h. So he wishes to observe the entire wall starting from W right up till W dash. He wishes to observe the entire length of the wall on the mirror that is placed in front of him. The question is, what must be the minimum size of the mirror with respect to the length of the given wall, that is h, or the height of the given wall? In this case, what you observed is that you obtained the length of the mirror with respect to the height of the person, and it must be half the length. But here the conditions are different. The person is standing in the middle of a room, and he wishes to see the entire wall um, behind him in the mirror that is placed in front of him. So I leave you with this question. I hope you try it and answer me. You can consider the eye of the person the same case of reflection. Uh, do it as you like, but try to obtain the answer so that we can move ahead in the ray optics or geometrical optics case. Till next time, thank you for watching.